Se va a proceder a la solemne investidura del doctor honoris causa. El secretario general leerá el acta de nombramiento como doctor honoris causa del doctor Paul Lecoq.
El Consell de Govern de la Universitat Politècnica de València, en la sessió del dia 22 de desembre del 2022, presidida pel senyor rector, a proposta de l'Institut d'Instrumentació per a Imatge Molecular i amb l'adhesió del senyor José Capmany Francoy, director de l'Institut Universitari de Telecomunicació i Aplicacions Multimèdia, els senyors Francisco José Mora Mas i Francisco Javier Saiz Rodríguez, professors del Departament d'Enginyeria Electrònica, els senyors Antonio Hervás Jorge i Samuel Morillas Gómez, professors del Departament de Matemàtica Aplicada, el senyor Ignacio Blanquer Espert, professor del Departament de Sistemes Informàtics, el senyor Pablo Botella Asunción, científic titular del Consell Superior d'Investigacions Científiques de l'Institut Universitari Mixt de Tecnologia Química, el senyor Filomeno Sánchez Martínez, investigador científic del Consell Superior d'Investigacions Científiques de l'Institut d'Instrumentació per a Imatge Molecular, el senyor Lluís Martí Bonmatí, director del Departament de Radiologia de l'Hospital Universitari i Politècnic La Fe, el professor Samuel Ting, del Departament de Física de l'Institut de Tecnologia de Massachusetts, i el senyor Frederic Bordry, director d'acceleradors i tecnologia de l'Organització Europea per a la Recerca Nuclear, va adoptar per unanimitat l'acord de nomenar doctor honoris causa per la Universitat Politècnica de València el senyor Paul Lecoq, de la qual cosa, i amb el vistiplau del senyor rector, en dóna fe en València a 3 de març del 2023.
El padrino, doctor José María Benlloch, será el encargado de pronunciar la laudatio del doctorando. Tiene la palabra.
Muchas gracias, señor rector magnífico, señoras y señores. Paul Lecoq was born in Lille, the same place as Charles de Gaulle, but he was also born the same year and the same month as the communist Chinese Revolution. And as we will see later, there is a link. He was a brilliant student at high school where he prepared to pass the exam. What? It's gone. Okay. Where he prepared for the exam of the Grand École. So he went to the École Polytechnique in Grenoble. I have to say that the Grand École were created by Napoleon, so it's mainly a military school. However, the majority of the people don't go to the defense, to the army, but they are currently running big companies, banks, or have top-level positions in different ministries. So Paul didn't go to the army and didn't go to the to the banks. So, but he did something probably more interesting. So he did when he entered at the school. Then he met the director of the school, which at the time was Louis Neal, and he told him, "I understand that you are interested by research in physics and astrophysics. You are at a good place. But I ask you to also register at the university and to run the two systems in parallel, like the Chinese, two systems. It will be much work for you, but at the end you will have the double diploma, the PhD, and also engineer the Grand École. But the next year, his director got the Nobel Prize That was very good. This is the first time that Paul started working with Nobel Prize. Then, for his PhD thesis, he went to the Université de Montréal, and then he was hired after finishing the PhD by CERN, where he started working with Samuel Ting, in the field of scintillating crystals. This is Samuel Ting, and the same year, Samuel Ting got the Nobel Prize for the discovery of the gypsy particle. The gypsy particle, I was called later. So we see here a pattern. You know, whenever Paul goes to some new institute and goes to work with somebody, that guy gets a Nobel Prize. And this is very good for us because he has come to our institute, and so we hope that the young people that are working with him, Antonio, Andrea, Laura, Marta, etc., probably they will get also a Nobel Prize. So this was very important discovery because it was the third quark. Before there was only U and D, so there was protons, neutrons, etc. So this was the first one that was not into a proton or a neutron. That was the charm particle. But then, later, it was found the bottom quark by Leon Lederman. And Samuel Ting, who was very ambitious and wanted to get a second Nobel Prize, he wanted to find the top quark. So he designed a new detector that was the L3 detector. And there, Paul worked a lot for the detection of gamma particles and and electrons as well. And so he started to work on new crystals, which is his field. It's VGO crystals, but there were very few of them and with very pure quality. So he went to meet the discoverer of the inventor of the VGO, Marvin Weber, who worked at the same laboratory where in December was produced the first nuclear fusion with Q bigger than 1. And also went with his boss, with Sam Ting, to Shanghai. And you can see here with Paul, with Sam Ting, and also with Jiang Zemin, who was at the time the mayor of the city of Shanghai, and later became the president of China. And he was also with John Dunstan, who was at the time the president of the Chinese Science Academy. And he introduced him to Dr. Guo. You can see here in the Chinese newspaper. Maybe you don't read them, but you can read in English. No, not because it's too small. But you can see here Paul working with Dr. Guo. And they developed this new technology for mass production of VGO. And this was completely instrumental for the running of the L3 detector. You can see here the L3 detector. Okay. So then the experiment finished with successful measurements of the Z resonance. And then there was the LHC challenge. The top was later found at Fermilab. The LHC challenge was to find the Higgs boson. And for that, it was very important, critical, to get the measurement of the gamma particles. And for that, VGO was not enough, because VGO is not dense enough, and especially is too slow. You need to get many particles, and in order to do that, the crystal light has to be very fast. So He had studied several crystals, produced several crystals, and here's the first proposal that he wrote for these crystals for the LHC. And he formed a collaboration of many people with different, it was a multidisciplinary team of 100 scientists. At the end, they published almost 700 publications and more than 70 PhD theses. So, but then a new photodetector appeared with some gain, a factor 10. Before there were no photodetectors with any gain. So he developed this new crystal. This was his idea, which is lead tungstate that was fast enough and dense enough for the LHC. So at the beginning, he was trying with cerium fluoride, but this was not fast enough. And so here's the mass production thing. It was really a big problem that he was instrumental in solving. And you can see here how it was installed in the year 2008. And finally, in 2012, mainly with the detector that he developed, the Higgs was found at the CMS detector. He also organized many conferences. Some of them, one of them was here in this university in the year 2003. And the first one of all of them made two major announcements. One was this new crystal that was essential for the discovery of the Higgs boson, and the second one was LSO, which is the detector the crystal that all scanners, PET scanners, currently use. So this is very important. So one thing is fundamental science, and the other thing is medical application. So in conclusion, before the work of Paul Lecoq, the science of scintillators was almost non-existent. But he formed a multidisciplinary team of experts around the world, and for that purpose, he created the SCINT conferences and also the Crystal Clear collaboration, which allowed the mass production of high-quality scintillating crystals with a high impact in high-energy physics and medical imaging. Amongst other benefits, that allowed the discovery of the Higgs boson in 2012. And he has also promoted the technology transfer to industry and medical imaging. Thank you, Paul. Así pues, tenidos en cuenta y expuestos todos estos hechos, dignísimas autoridades y claustrales, solicito con toda consideración y encarecidamente ruego que se otorgue y confiera al doctor Paul Lecoq el supremo grado de doctor honoris causa por la Universidad Politécnica de Valencia.
Se va a proceder a investir al doctor Paul Lecoq como doctor honoris causa.
Tothom dret, per favor.
Of the Universitat Politécnica de Valencia, at the proposal of the Institute for Molecular Imaging Technologies, with the institutional and individual endorsements included in the minutes of the Council, and in testimony of the recognition of your relevant achievements, you have been awarded the title of Doctor Honoris Causa. By virtue of the authority vested in me, I confer this title and impose on you as a symbol the laureate biretta, venerated distinction of the highest academic rank. Wear it on your head as the crown of your studies and merits. Receive the signet ring that antiquity gave in this venerable ceremony as a symbol of the privilege of signing and sealing the opinions, consultations, and censors of your science and profession. As well as these white gloves as a symbol of the purity that your hands must preserve. One and the other are as well symbols of the distinction of your order. Because you have joined our University Senate, receive now in its name, Dr. Paul Lecoq, the fraternal embrace of those who are honored and delighted for being your brothers, sisters, and colleagues.
Podeu seure.
Tiene la palabra el doctor Paul Lecoq.
Señor Rector Magnifico, señoras and señores. First of all, I apologize for not speaking Valencian, nor Catalan, not even Castilian. I recognize that it is a clear sign of lack of education, and I am even more honored to have been selected, in spite of this, to join your prestigious university. Professor Benyok kindly reported on my past career, and I just would like to conclude the ceremony by saying a few words about how I see the future of scintillators. Scintillators are used in many applications. In medical physics, they are somehow the eyes of the PET scanners. In particle physics, as Professor Benioff said, they have played a fundamental role in the discovery of the Higgs boson in a huge detector made of 100 tons of scintillating crystals. But they are used in many other applications: nuclear plants and nuclear waste monitoring, baggage screening in the airport, border inspection, and all kinds of non-industrial, non-destructive industrial testing. And in all these applications, the function of the scintillator is to detect ionizing radiation. And when we want to detect something, the first question to ask is what we want to see. And in the case of ionizing radiation, what matters is, first of all, to know where the event took place. But second, to know what was the energy involved, what was the type of the particle that was producing the interaction with the scintillator. Was it an electron, a neutron, a proton, an X-ray photon, a gamma-ray photon? But we see emerging a growing demand for also precise time information about the event. And this is boosted by a number of emerging technology which allows now more and more to reach a precision in the timing domain at the level of the picosecond. And time is very important because you know that in our universe, space and time are strongly correlated. And if you have a good precision on time, by time of flight technique, you can infer good precision on the location of the event. But also, time helps to have a better information on the energy and on the particle identification. All the people who have played with a photo camera know that good timing resolution brings more information on the image. So this is quite important, and I think that will be the main subject of the future for the development of these new sensors. If I just focus a little bit on medical imaging and on PET imaging, the state of the art today in terms of timing is of the order of 200 picoseconds. What we are trying to do, and I will explain a little bit how, is to reach a timing resolution of the order of 10 picoseconds. So it's a factor 20-fold improvement in timing, which directly translates in factor 20 improvement in the sensitivity of the PET scanner. And if you have sensitivity of the PET scanner, which increases by a factor 20, this can be used in many different ways, but one very important one is to reduce the dose injected to the patient by a factor of 20. And then we can ultimately dream of an exposure of the patient during a PET scan for a whole body PET scan at the level of 0.03 millisieverts, which has to be compared to the annual natural background that you receive depending on the location where you are living, between 3 and 4 millisieverts. So 2 orders of magnitude higher. It can be compared also to a return flight San Francisco to Europe at the level of 0.1 millisievert. So allowing to reduce the dose injected to the patient at such a small level opens also the PET application to new categories of patients which cannot be concerned today because of the risk of the radiation, and particularly in the pediatric, neonatal, and even prenatal domain. So this is what this slide quickly shows. In order to do that, you need a very good scintillator. A good scintillator for detecting ionizing radiation is a detector, first of all, which is very dense. In order to absorb the energy of the incoming particle, the incoming radiation, in the smallest possible volume of detector. And this is important for also the quality of the measurement, but also in terms of cost. But you need also the scintillator to be as bright as possible, to provide as much photons, scintillating photon as possible when ionizing radiation interact with it. And you need this scintillation signal to be as fast as possible, because again, we are interested to have good timing. And you need to have a good energy resolution, which is somehow related to the light yield that the scintillator will produce. So if I look at the best scintillator known today, and I represent each of them by the sphere or circle, the diameter of which is proportional to the density. And as I said, we want to have as dense as possible material. In a two-dimensional plot, in the logarithmic scale, so this is important, on a horizontal axis, the light output, on the vertical axis, the decay time, so in fact, the information about timing, and a color which represents the energy resolution, and we want to have it as dark as possible. So there are two interesting crystals here. I don't know if I can show directly. Yeah. This one is lead tungstate. It's the crystal that we have used to detect the Higgs boson. As you see, it's quite dense, a density much higher than steel, 8.28 grams per cubic centimeter, still very transparent, which is a challenge in itself. It is very fast, about 10 nanosecond decay time. It has a low light yield, but it doesn't matter at high energy physics, in high energy physics for the Higgs boson, because the particle to be detected has very high energy. So in fact, even the intrinsic light yield is small, the number of scintillation photons is high. So that was not a big problem. So this is a very important crystal. There is another one, which is this one, which is the lutetium orthosilicate that José María Benyoc mentioned before, and which is the crystal today commonly used in PET scanners. But what we would like to have is a crystal which is 10 times brighter and 10 times faster than this LSO, so a crystal in this category. And unfortunately, we have good reason to believe that there are some physical barriers that will prevent us to discover such kind of, or to develop such kind of crystals. However, the fantastic world of quantum physics can provide some solution. I just give you an example. When you have ionizing radiation interacting with matter, this ionizing radiation will produce electron-hole pairs. So that if we eject an electron for an atom, it will remain a hole behind that. But this electron and hole are bound in a system which is called an exciton. And this is the recombination of the exciton which will produce a scintillation photon. This bound system, electron-hole pair bound system, has a certain dimension in a crystal, which depend on the crystallographic field. This dimension is defined by the so-called Bohr radius. So if, in contrast to a bulk scintillator, so large size scintillator, where the electron-hole pair will have this extension, this special extension, if I confine this exciton in a nanocrystal, the size of which is smaller than the Bohr radius, then I will strongly enhance the recombination probability between the electron and the hole. And therefore, I will have a much faster recombination process. This is what I want. But not only that, if I manage, instead of having one exciton in my nanocrystal, to have 2 excitons, then I multiply the recombination rate by a factor 4. And therefore, I decrease the decay time by a factor 4. If I have even more, 3 excitons in the same nanocrystal, I multiply the recombination rate by a factor 9. So it's going like the square of the number of excitons. And this has been proven experimentally. One of the nanocrystals we are working with is a CDSE nanoplatelet, so we confine in only one direction in order to increase the probability to have several excitons in the system. If I excite this nanocrystal, this nanoplatlet, at a relatively low level of excitation so that I can create only 1 exciton in the system, I have already quite a fast recombination, 1 nanosecond. As you can see, this is a straight camera image. The vertical scale is the time. So you see this long line, actually, but this is in picoseconds. So long line, typically you have 1 nanosecond decay time, which is already 10 times faster than the very fast lead tungsten crystal that we have used in the CMS experiment for the Higgs boson. But now if I increase the density of excitation so that I can create on average 2 excitons, you see that the decay time drops to 200 picoseconds. And if I further increase the excitation density so that I can create on average 3 excitons in my nanocrystal, the decay time drops to 69 picoseconds. So I have a way to produce extremely fast scintillator by quantum confinement. So this is very interesting. We are looking at different nanocrystals of that sort, but one family of them, very interesting, is the so-called metal halide perovskite. And I'm glad to pronounce this name here, because you have here at UPV a very great experience on this kind of crystals, the perovskite, because they are also very much used for photovoltaic application. But in our case, we want to use them for scintillation application. But in fact, we want also to benefit from the expertise here at UPV to develop this nanocrystal. But this is not all. Beside the nanocrystal, you have also a number of nanophotonic features, so again, in the nano world, I would say, which are quite interesting. The majority of the material, the majority of the crystal that we are using are, as we say, isotropic material. What does it mean? It means that the electric and the magnetic permittivity is positive and about equal in all the 3 spatial dimensions, X, Y, and Z. And therefore, the dispersion relation, optical dispersion relation in this material leads to isofrequency curves which are spheres. So what does it mean? It means that at a given frequency, the number of optical states which are allowed to couple the ionizing radiation, incoming ionization radiation, and this material is contained between 2 spheres, which this is what you can see in red here in this picture, 2 spheres with slightly different diameter corresponding to 2 different frequency of the scintillation. And obviously, between 2 spheres, you have a finite volume. And therefore, you have a finite number of optical states which can be coupled to the incoming radiation. On the other hand, if you have a material, or if you can design a material, and we can do it, where at least one of the permittivity vector is negative, whereas the other one are positive, then the isofrequency surface is not anymore a sphere, but it is an hyperboloid. This is what you can see in a blue-green color here. And the big difference is that the volume, which is contained between 2 hyperboloids at 2 different frequencies, is not anymore finite. It is infinite. And the great advantage of this hyperbolic metamaterial here is that locally you can increase the photonic density of states in the structure by orders of magnitude. So basically, when an incoming particle will come, it will produce much more optical photon. And this is a prompt optical photon. This is the one we are interested in. And this has fantastic and I would say sometimes surprising consequences if you are only concerned with classical physics. And this is the magic of quantum physics, in fact, is to open new doors and new possibilities. And just to give an example, it can boost by several orders of magnitude the production of Cherenkov photon when a particle is crossing this medium. So you know Cherenkov light is similar as the bang emitted by an aircraft going at a speed faster than the speed of sound in air. But similarly, in a medium, whatever it is, if a particle is traveling faster than the speed of light in this medium, which is actually the speed of light in vacuum divided by the index of refraction of this medium. So if the particle is going faster than the light in this medium, it will emit very promptly Cherenkov photon. But it requires the particle to cross this threshold in speed. The magic of the hyperbolic metamaterial is that you don't have any more threshold. Even a very slow particle can emit Cherenkov photon. And this it completely breaks the standard rule of physics, but it is still true. And thanks to us. So this is another very, very interesting feature that we want to take advantage of. Last but not least, I would say that there is, in parallel with that, a lot of progress in crystal manufacturing. So not only we can grow not standard ingots, as was done since decades, but we can grow scintillating fibers. I have in my office a fiber of lutetium aluminum garnet, which is 1 meter long, which is pure monocrystalline and 400 micron diameter. And I can bend it, I can make a circle about of it. So this is fantastic as well. But you have also much more progress in the production of scintillating ceramics. And there is also, we start to progress very well also in the possibility to produce crystal by 3D printing with very fine structuration. So this is the image that you have here at the micron level. So that opens also a number of ways in the way to structure the material. So capitalizing on that, we have developed the concept of meta crystal or meta scintillator. Meta from the Greek meta, which means going beyond the possibilities of standard physics. And this is a deep tech approach, capitalizing, as I say, on a number of emerging technologies in order to produce a system which is a multifunctional scintillator in contrast to the bulk scintillator that we have used so far, which combine the high stopping power which is needed of already well-known scintillator to the prompt emission of nanocrystal combined with some nanophotonic features in order to have a nice management of the transport of the photon from the scintillator to the photodetector. And the principle is actually relatively simple. You combine in the same system, instead of having a bulk scintillator, you combine, let's say, as I say, heavy dense scintillator to allow the conversion of the ionized radiation with layer or some parts of this metascintillator, which is made of nanocrystals or this kind of hyperbolic metamaterial, where the light will be emitted very promptly. So basically, the energy which is leaking from the dense scintillator to this fast scintillator part, will produce, as you see, an excess of scintillation photon in the first part of the pulse, of the scintillation pulse, which is just, if you look at the scale, a fraction of nanosecond here. So you will have an excess of photon in this the very, very beginning of the pulse, which will allow you, or allow us, to have a very precise time tag of the event at the few picosecond level. This is our goal. We have different ways to integrate these different materials, and we are working on this in a strong, close collaboration with the group of I3M here in the UPV. We have 1D integration, where basically we have plates of different kind of materials that we stack together. We can have a more elaborate system with a 2D integration, so we use dense scintillating fibers that I mentioned before, because we know how to produce them. And in the holes in between this fiber, you insert so-called photonic fibers, which the core of them is loaded with nanocrystal in order not only to produce prompt photon in the nanocrystal, but also to transport this photon efficiently in the photonic fiber in the direction of the photodetector. So if we can use this, if we can develop this material, and we are in a good way, and we have already made a lot of progress in this direction, that will have an impact on PET imaging in the medical domain. PET is a fantastic medical imaging tool which has a very, very high sensitivity at the picomolar level. Just to tell you, the sensitivity is 1 million higher than MRI. MRI has its own merit, very good spatial resolution, etc. But in terms of sensitivity and having the possibility to access very tiny metabolic processes in the human body, PET is unbeatable. The recent development in terms of time-of-flight PET, the standard, the state-of-the-art being at the level of 200 picoseconds, allow PET to be even more sensitive and to be even more powerful as a medical imaging tool. But our work in the direction of 10 picoseconds will boost the performance of PET beyond your imagination. Conclusion. There are a number of disruptive technology, and particularly in the domain of nanophotonics. And here again, I'm glad to say that you have here at the UPV extraordinary expertise in this domain that I really would like to exploit as much as possible. And now you have the legitimacy for doing that. Thank you for that. This allows to open new perspectives for new intelligent multifunctional sensors. As a French physicist, the mother of which was born in Corsica, like Napoleon, I cannot resist to the pleasure of citing Napoleon, a very famous word of Napoleon. Impossible is not a French word. And I will illustrate that in a small 2-minute movie, if you still have time, if you are not too tired, with a different example. So after the invention of cinema by the Lumière brothers in Lyon in the year 1895, George Méliès, one of the first movie makers, reactivated the race for the moon dream, which was initiated by the famous French writer Jules Verne 40 years before. That was, of course, a dream at the time. but it became a reality in 1967 with the Apollo mission. Similarly, autonomous cars were a myth in the beginning of the 20th century, as you can see here. But they became a reality in the beginning of the 21st century, thanks to Google and other people working hard in this direction. The same for Visiophone. It was a myth in the beginning of the 90s. It was still a myth in 2001 when Stanley Kubrick produced his movie Space Odyssey. But it became a reality now. You have this on all your smartphone. So metascintillators, they were a myth a few years ago, but they are becoming a reality here in Valencia. And I would like to thank you all, but I would like at this stage to take the risk of disgracing myself by daring to say a few words in Spanish. I'm very sorry because at the school I learned Latin, German, and Russian, but Spanish was not in the list. So forgive me for my accents, but I'll try. Quiero dar las gracias a la Universidad Politécnica de Valencia por su acogida. También al rectorado por otorgarme el grado de doctor honoris causa. Felicitar al equipo con el cual estoy trabajando. And now, even more difficult for me, I try in Valencia. I també tots els valencians i valencianes que nos han rebut tan amistosament. I terminaré gritant Visca València!